वहाँ तुम्हारा इंटरनेट ज़्यादा ले रहा है अभी काम। बिस्मिल्लाहिर्रहमानिर्रहीम। आप लोग आ गए? हेलो, ये सलमान साहब आ गए?
जी सर, अस्सलाम वालेकुम।
वालेकुम अस्सलाम। आपको इस वक्त स्क्रीन पे नजर आ रहा है? चाहिए हमारी बुक नजर आ रही?
सर
शेख
अभी
वाली
इस वक्त आ रही है नजर
बुक नजर आ रही? ठीक,
जी
ओके।
बिल्कुल।
अच्छा, वो मैंने ना ये मैं ख्याल स्टूडेंट्स आ ही जाएंगे, वो मैंने ना रिकॉर्डिंग का सिलसिला बंद ही कर दिया, क्योंकि ना वो फिर वो आवाज़ जो है ना वो कभी भी उस लेवल तक नहीं पहुंच पाती जो लाइव आवाज़ होती है। रिकॉर्डेड आवाज़ ना, वो मुझे तो यही लग रहा है कि वो उसका तेज़ होना बड़ा मुश्किल है या लाउड होना मुश्किल है, वो हल्की रहती है। फिर वो जूम पे चलती है, जूम इस पे आता है तो और हल्का हो जाता है।
सर ये ठीक है, ये मुनासिब है। जो हमारा लाइव इंटरेक्टिव सेशन होता है जैसे लेक्चर रूम में होता है, ये ठीक है, क्योंकि रिकॉर्डिंग तो
हाँ
इसकी होनी है। इन एनी केस हमें इसका रिकॉर्ड तो मिल जाएगा। अगर किसी
हाँ,
ने लेक्चर
बिल्कुल
रिवाइज करना हो तो वो देख सकता है।
जी बिल्कुल। मैंने वैसे ये कि सारे नोट्स वगैरह बना लिए हैं, वो इंशाल्लाह बाकी जो रह गए वो अपलोड भी हो जाएंगे, वो साथ आप देखते भी जाएंगे और ये इंशाल्लाह दोनों काम साथ साथ हो जाएगा।
बिल्कुल ठीक है। सर आपने कोई इसमें अपना जैसे वो टीए होते हैं या आरए होते हैं, इस तरह नहीं है आपके पास जो इस तरह की चीज़ें मैनेज करें? क्योंकि ये तो इसमें तो डाटा मैनेजमेंट और ये इस तरह की चीज़ें बड़ा लंबा चौड़ा काम है,
जी जी,
नोट्स
वो
बनाना।
फिर जी जी, वो तो आप हालात हैं कि अंडर ग्रेड में कोई अवेलेबल नहीं तो ग्रेड में कहाँ से होगा। हालांकि अंडर ग्रेड तो वो भी एक्रेडिटेड है, उसके
जी
लिए तो इनको देना चाहिए था, उसके लिए अवेलेबल नहीं है सब। तो जो फाइनेंशियल क्रंच है, तो इसमें तो बहुत ही मुश्किल है कि मास्टर्स लेवल पे हमें कोई मिले।
यानी कि डिपार्टमेंट लेवल से सपोर्ट नहीं है।
हाँ जी, डिपार्टमेंट में मतलब वो है ही नहीं, स्टाफ ही नहीं है जो दे सकें अभी तो।
स्टाइपेंड की नहीं
आ,
है।
हाँ, स्टाइपेंड है और भी बहुत सी चीज़ें हैं। अभी अंडर ग्रेड ही नहीं पूरा हो रहा तो ग्रेड कहाँ से होगा? ग्रेजुएट तो आपका ओबी पे है ही नहीं सर्टिफाइड।
हाँ जी बिल्कुल ऐसे ही।
जी जी, चलिए खैर हम स्टार्ट करते हैं अल्लाह का नाम लेके, बिस्मिल्लाहिर्रहमानिर्रहीम। सो इन द लास्ट लेक्चर, इफ यू कुड रिमेंबर, वी हैड कवर्ड till equation 3.59, and after lengthy derivation we were able to show that the probability of error is bounded by 15 over SNR square. So this was the probability of error of our new codes, okay, which I discussed, uh, rotational codes. So they were trying to give us both diversity gain of reputation coding as well as coding gain. So you could see here this SNR2 is actually representing the diversity gain, while this 15 actually is giving us the coding gain. Now let us have more insight into this equation. First of all, we know this 15 was driven from the uh, previous equation 3.57, where it was 48 divided by minimum of delta Aj, where if you could remember, so these were all product distances, delta AB, AC and AD. So we need to know why these distances are so important, and we can see one way that they are important because they will come in this equation and hence they will determine the order by which the probability of error is governed or uh, is given by the order given by these deltas. So here we will try to understand this importance of product distance with respect to our previous knowledge. Now, if you could remember, previously we had studied the probability of error for a non-diversity system as well as a diversity system. If you could go back into our previous lectures, just as sake of revision so that we are able to understand it properly, you could see that we had learned that the probability that h square is less than 1 over SNR. This was the case when there was no diversity. Okay? There was only a single channel. There was no time diversity. The symbol was being sent only one. And we had learned all of that. There we had studied actually that when we will have error in these types of fading channel, this will happen when h square multiplied by SNR is much less than 1. Because you could learn, because if you could see that our probability of error came out to be 2 into h mod square SNR. So if this factor h mod square is very large, then you can very well see that the argument of Q function will be very large, and hence you will be integrating at a larger number, and hence the area under the Gaussian curve will be small. All right, but if this same factor is very small, in that case argument will be very small, and the area under the Gaussian curve will be large, hence error will be large. This Q function was giving us the error for non-diversity systems, and we said that the error becomes large even for high SNR. Event will become large when our h mod square SNR is less than 1. So when it's less than 1, you can see the error will become large. And then we saw that for large SNR this goes 0. So we can actually relate this, that for large SNR the event of deep fade was this, and the probability of going to deep fade was 1 over SNR. This was a very fundamental relationship. Now this relationship came again when we were studying diversity. Okay. So the first time when we studied diversity before our this corona break, again you could see the error was coming out to be 2h mod square SNR. See the difference. There it was h mod square. Now it is h vector mod square. This is double sign. This is representing a vector. Why it is a vector? Because now your single data is being sent through diverse paths. If we are using transmit diversity, so we will be and let us say this was for repetition coding. So we are repeating the same symbol many times. 10 times, so the length of this h will be 10. All right. So in that case, when will we be in error? When this total factor h mod square SNR will be less than 1. Okay. Will be less than 1. You can see error probability will be very large. And there was a long proof, but very good thing is that this book gives us an idea about Thumb's rule. The conclusions. One set of conclusions that you come after a long set of mathematics. Other conclusion is that you can develop your intuition, and those intuitions can lead you to those Thumb's rules. And there we could see that probability that h mod square will be less than 1 over SNR. They will be giving us deep fade for these diversity systems, and they again come out to be 1 over SNR L. Okay, mathematics we are not going because we have done all of that. Just to, and if you could see this paragraph, you was actually repeating all of that. That if for one path you have 1 over SNR and all the paths are independent, then probability that all the paths they go into deep fade will be 1 over SNR times 1 over SNR into L. So 1 over SNR L. Okay. So this was what we have learned. I have just tried to put all of that in form of notes. So I have taken the picture of through CAM scanner so that every one of you could have a better view. because you know, I realized once we take the view with the help of the camera, so that is actually angled or a lateral view, but with the cam scanner this gives you a very straight picture. So again, now let us try to uh, what we have just learned through concepts, apply this in terms of mathematics. So we have learned from equation 3.31 that for rotational codes, probability of confusing A with B, given that H1 and H2 are known, is given as follows. Okay? It is not just H1 or just H2 or H1 mod square. It is actually H1 D1 plus H2 D2, because these are rotational codes. Their derivation was, or their outputs are different. Now, we have learned when we were doing non-diversity systems that, so probability of this being less than 1, which means when we will have a large noise power. So when channel gain will be much less than 1 over signal to noise ratio, or when we will be in D phase, is 1 over SNR. Similarly, we learn that for diversity systems, reputational codes, so as shown in the explanation, that it comes out to 1 over SNR. There your Q was given as follows. Now what comes here? Here you can see that we have this equation. All right. So again, trying to write it in the same form as we have written in the previous 2 times. So this will come out to be 1 over SNR. Probability of this being less than 1 over SNR. Okay. This implies that this value and this value, they both must be less than 1 over SNR. All right. And probability of this being less than 1 over SNR, okay, will be equal to what? Will be equal to the value, as we have seen previously. Probability of H being less than 1 over SNR was 1 over SNR. This was a fundamental rule that we learned many times. Probability of H mod square being less than 1 over SNR was 1 over SNR L times. Okay. 1 was 1 over SNR, then it was L times. So for single, this will be 1 over D square SNR. Similarly, for this will be again 1 over D square SNR. Okay. Probability of both will be less than 1 over SNR. Okay. So coming back to the book. So he says that confusion is governed by this distance, and this distance, so he says, has to be the order of 1 over SNR. Okay. You can say order, but it is also right. But mathematically we will write less than 1 over SNR, because once we say something is less than 1 over SNR, this means its order is 1 over SNR. You know, or what is order? Order is actually a function that actually governs, or that actually covers this mathematical function. So 1 over SNR is covering. You can either say order or you can say less than. So mathematically we will be writing less than 1 over SNR, as we have been doing in the past 2 instances. So if this total is governed by 1, this means each of them must be less than 1 over SNR or of the order of 1 over SNR. Okay. And this happens with the probability approximately, because we know again that these are independent, H1 and H2 are independent. All right. So as we have done previously, that one is less than 1 over SR, other is less than 1 over SR, then combined is less than 1 over SNR square. So here we will have again multiplication, because they are independent processes. 1 is less than 1 over D, H1 mod square is less than 1 over D, H2 is less than, so the joint will be product, and you know it will come out to be as follows. So you can see diversity gain is still there, 1 over SNR L times or SNR square is still there. But we have these two things, which are D1 mod square and D2 mod square. So D1, D2, they have to be some value. For rotational codes, they have to be some value, so that you are also getting diversity gain. Okay, but we know these will be also giving us some other gain, which is called the coding gain. Now let us try to compare the advantage given by rotational codes, okay, over another codes, let us say over PAM modulation, pulse amplitude modulation, or repetition scheme. We will be using PAM with repetition scheme. Let us try to understand in detail. So first of all, we want to keep the bit rate constant, because if you could see here, we had actually 4 code words in rotational codes. Okay, we had, you could see, at these 4 code words. All right. So if you have 4 code words, so how many bits will be required to represent each code word? If you have 4 symbols, you will have 2 bits. All right. So if you want to compare this with repetitional, we also must have a scheme that requires 2 bits. So that is why we use 4 PAM. All right, we use 4 PAM, and you know, PAM is actually over real symbols. So you'll be using the repetition scheme over 4 PAM. This means that we have, if I send B, then at another time interval, when I will, after the coherence time, I will again send B. Similarly, if I send minus B, I will again send minus B. 3B, I will again send 3B or minus 3B, like that. Okay, so it is repetition using PAM. So it is using 4 PAM symbols, but it is repeating them. Okay, so he has also given us a figure so that we can understand. These are our rotational codes. So you can rotational codes, but actually to A minus A minus A, but you could rotate them. You know, if you could multiply that with R matrix, and you could rotate them to any angle depending on your theta. But you could see here what is happening. Here there is no rotation. If it is B, then you have to repeat B. 3B, repeat 3B. So they are only on a single line. This is first symbol, this is second symbol. Symbols are in time. This is also first symbol, second symbol, but the symbols can be rotated. Okay. But there you have to place them on a single line, because there is no theta phi or rotation available with PAM. Acha. The pairwise error between the 2 adjacent code words is given as follows. So this is the same equation that we have driven in case of rotational code. If you compare 3.61 with 3.51, this thing, you could see it is actually the same. Right? SNR over 2, H1 mod square, H2 mod square. Same here, SNR over 2 mod, like this. Both are same. But what is the difference now? So even if you're using rotational, or if you are using PAM, you will be, you can use, you do the whole derivation for PAM with these symbols, you will again get this. But what will be the difference? SNR is different. What is different? SNR is different. Why SNR is different? Because in this case now, my SNR will be given as the SNR of PAM. Alright. So how can I write my SNR of PAM? This is the signal to noise power ratio, or signal, or average signal to noise ratio. What was the average signal to noise ratio for rotational codes? Let's see, in rotational codes, when we were studying all of this thing, so you had only 2 symbols, A or minus A. You don't had 3A, 3B like this. You had just A and minus A. You had no choice. Actually, you were using BPSK. You were using BPSK symbol. Hari, what is the, so if I ask you, for example, so I am, let us ask anyone can anyone answer that? What was the signal to noise ratio for BPSK? I know it's a long time we have to write. Salman Yusuf, can you shed some light? You can unmute yourself.
सर वो बीबीएस के अगर आप मुझे अलाउ करें तो मैं सर बुक से भी देख रहा हूँ.
अच्छा मुझे आपकी इतनी आवाज वाजे नहीं है. मैं सिर्फ कह रहा हूँ कि क्या डू यू नो व्हाट इज द सिग्नल टू नॉइज रेशियो फॉर बीपीएसके? If you don't know, no problem. Just I'm a cursory question, because if you don't know, then I think I should explain so that everyone is at the same level. Do you remember how do we found the synchronization for BPSK?
सर काइंडली थोड़ा सा इसको एक्सप्लेन कर दीजिएगा. अभी मेरा बैक ऑफ द माइंड रिफ्रेश नहीं है, तो आप मुझे बताएंगे आगे तो.
No problem. You can mute yourself. No problem. Does anyone know? Anyone? Achha. No problem. No problem. Okay. You can all see the screen, I think, huh? Yeah. Now remember that for BPSK, signal to noise ratio was A square over N naught. Because why? The symbol is plus A and minus A. So what will be the power? A square plus A square minus A square A square. Alright, what will be the average signal power? Alright, let's say I send million symbols into A square divided by million. I will get A square as the mean value. Signal power mean value is A square. Now what is the noise power? So we know noise is N naught by 2, but both in real and imaginary domain or channels, IQ channels, whatever you can say, total power we have done, how to calculate, it comes out to be N naught. The signal noise ratio was A square N for BPSK symbols. Now let us try to see. Yes. Yes. So what will be the signal to noise ratio for PAM? For what will be the signal for PAM? If you can remember, it was 5B square. Does anyone remember how did we found this 5B square? Hi, does anyone remember?
जी सर, वो हमने सिंबल्स को एक लाइन पर ड्रॉ किया हुआ था ना, उसमें पावर थी -3B थी, फिर -B थी, फिर आगे इसी तरह B थी और आगे थी, और उसके बाद सर हमने उसके जो थी रीजन्स बनाए थे दो के डिसीजन बाउंड्रीज क्या बनेंगी.
वो तो खैर आप आगे बहुत आगे चल के इतना मुश्किल नहीं कह रहे. मैं कह रहा एनर्जी निकाल लीजिए ना. अब ये देखें पैम सिंबल्स हमारे पास यहाँ शायद पिछले में बने हुए थे. अगर ये इधर आ जाए ना तो मैं आपको, हमने पैम इसमें पहले भी किया हुआ है. ये देखें ना. These were the same. How did we find? हाँ जी, 3B square 9B square plus B square plus B square plus 9B. This comes to be 20B square divided by how many symbols? 4. It comes out to be 5B square.
5B square.
So 5B square was the average signal power. Ari, what is the noise power? What is the noise power for PAM? It remains same because noise is N naught by 2, N naught by 2. What can we do further? If we cannot do anything, N naught by 2, N naught by 2 we have done this, So SNR is changed only, which is 5B square over N naught. Okay? So this is changed and rest of it will not be changed. Now, second question. Haji, what is the value of D1 or what is the value of D2? Alright. Now, what was D1, D2 for our case? For rotation codes, we in the last I showed you xa1 minus xb1 over a normalized distance. The same thing we have to do here to find that. So distance, for example, between 3b and minus b, or between minus b and plus b. Okay. There you were dividing it by a, but here you will be not dividing by a, but you will divide by which number you will divide by? For PAM, you will divide by under root of 5b square. There you are dividing by a, because under root of a square is a. But here you will be dividing by under root 5b square. So I have also done this. I can show you. How can I show you? Let us go into this thing. And I will stop share. And I will start sharing the. वो कहाँ चला गया? Adi, can anyone see this notes in respect to mathematical equations? Where I am moving my arrow. Everyone seen that?
Arrow freeze है.
Can you see this this figure?
अब आया है. हाँ जी बिल्कुल ठीक है. xa1 minus xb1 by b.
Yes. So please take it. So what is this? I apply my normalized distance for PAM. So you know, or PAM में है क्या? You have BB minus 3B. So let us say, you know, I take 1 3B. Adjacent to 1 is B, 3 positive. So 3B minus B divided by not B, divided by under root 5B. That is 5B square and under root 5B. And you know this BB and 2 over under root 5 is the normalized distance. You can also find the other distance D2, which is between B minus B, which will be again 2B. You will gain the same value of 2 over under root 5. Okay. Is that your understanding? Okay. So what should I do? I should come back.
सर ये नॉर्मलाइज का ये जो अंडर रूट 5 आता है सर.
हाँ जी.
सर ये डिस्टेंस उसका जो फॉर्मूले उससे हमने इसका डिस्टेंस निकालने दो सिंबल्स कितने में.
नहीं अच्छा आप अपने आप को अनम्यूट करें. आप अनम्यूट कर शोर काफी ज्यादा ना आप. हाँ जज़ाकल्लाह. देखिए मैं आपको ये समझाना चाह रहा हूँ. फर्स्ट ऑफ ऑल you should ask the question in English. As all the videos are being recorded, I should also try to speak as much in English. But once students start speaking in Urdu, I also turn towards speaking in Urdu. So we should all try to speak English, because this is a international university and lectures are being recorded, so they will be viewed everywhere. So we should all try. No problem if we are not able to speak correct English, but we should try to make our conversation in proper English. Now again, try to understand what I am saying here. Okay. So देखिए ना, this is the formula. T1 is first symbol, first element. Second symbol, first element divided by, actually it was A previously, but I just say alright, it will be B now. No, it will not be B. Previously it was A because the average energy was A square. Average signal power was A square and its under root was A. That is why I was using A in rotational codes. Here average power is 5B square, which I just told you how to find. 5B square. Okay? It was 5B square. So 5B square under root will be under root 5B. That is why I will divide by under root 5B. And the second question is why do I get this thing? Because you can see, if I show you, I stop share. I have to stop this sharing, then I have to show you the other figure. Stop share and then I do share of the book. Yes. So you could see here why 3b minus b, because you can see these were the, we are not using BPSK, we are using PAM. So one symbol, first symbol is 3b, or let us say here plus 3b, other is b. All right. So distance is 3b minus b. Distance will be 3b minus b. Other symbol is also 3b minus b. It will remain the same. Then you will have b minus b. So b plus b, it will again become 2b. 3b minus b is also 2b. So we will be just finding distance with the adjacent codes, with the adjacent ones, not b with this, because error probability is only given by with respect to the adjacent ones. All right. That is why I just told you. Stop sharing and then sharing. So that is why I was showing you this thing. It will be something like this. D1 will be 2 under root 5 and D2 will also be 2 over under root 5. You can do the calculations. All right. Let us go in the next step. So we have found D1, D2 for PAM repetition coding, as we found D1, D2 for BPSK rotational codes. So let us find the product distance for PAM repetition. So just apply the formula D1, D2 mod square. You can get the value. This comes to 16 over 25. Now put this value in the equation of the book. All right, which was 40. If you could see the book equation, I will. Okay. So in the book, we had already seen that in the last lecture. Yes. So it was for one, it was 16 D1, D2, but for combined it was 48. So I use this combined one. All right, this formula. All right, as we did in the previous case. No, there's no change till this point. Okay, everything is all right. So as we said, I take the minimum of them. So minimum of them, so it will be governed by minimum. This will become 3 times the minimum. This becomes 48, as we have done previously. All right, this comes here. So this value, instead of being substituted by the rotational code value, I am substituting this with the value given for PAM repetition coding. Okay. And so 16 over 25, I cancel and I get 75. Now please see what has happened. That now my error is of the order, or it is less than 75 SN, but previously it was 50 SN. Haji. So which is better, 75 or 15?
The 50 is better.
Which is better?
So probability error जो lesser होगी वो better होगी, जो lesser है.
15 will be better. Yes, you are right. Good.
Yes.
Yes. Good. Yes. Yes, Salman, you are right. Yes, it will be 15 is better, because you are basically, order of, or it is being less than by a greater number. This means its error probability is greater. Now, same thing, he has actually tried to discuss this in the book. But I think you won't be able to understand. First of all, I will show you the book. Okay? Then we can, if you are not able to understand, we can go to the mathematics. So he says here, you could see that sorry, this we have already done. So this we saw 0.25, it is different, and so rotational code has an improved coding gain over the repetition code in terms of saving in transmit power by a factor of delta 5. He says that for the same product distance, you are getting an additional gain called the coding gain over the repetition code, and because of this gain you are actually saving transmit power by a factor of under root 5. Now you will say, sir, how can you say that matlab ke, this has given us an advantage? All right, so I have yes, so this is actually here. So you can see here, see how can you actually write this. So so probability of error for PAM is 75, but for rotation is 15. All right, now what can I say? I can say, all right, for PAM 75 is 15 into 5. All right, so I take my 5 in the denominator. All right, so this means that for PAM, now remember this is also 15 and rotation is also 15. All right, so we have just tried to make the product distance equal, okay, so that we can compare the signal to noise ratio. Signal noise ratio is what? Signal power, noise power. So noise power is same everywhere. So a signal power, I just put this 5 in the denominator, so it is dividing the signal power by under root 5. So it is inside the square. So for PAM to have the product distance of rotational will require signal power for PAM to decrease by a factor of under root 5. Hence, rotational saves under root factor of transmit power. Vice versa, you can also see here that if I take for rotation, so I divide by 5, multiply 5, divide by 5, which inside square it goes under root. So what this tells me that so rotational to have PAM product distance, so that will require signal power or rotational to increase by a factor of under root 5. So here comes advantage in transmit power. Actually, where this transmit power has come? This has come alternatively from the coding gain. It is actually saving a lot of transmit power, and under root 5 is a huge factor. You can see it's 3.5 dB. And here I've just done this by myself, just take the ratios of their probability of errors. You can see the probability of error of PAM is less than 5 times the probability of error of rotation. So the probability of error of PAM is bounded or is of the order of 5 times rotational. Again, this gives a proof that rotational is quite better. Okay, so I think you are able to understand. Here he is. Now this mathematics is explained in words. Okay, why this is improving? This is improving because we are able to spread our code words in the whole dimensional space because of rotational codes. Everywhere we can. But for PAM, you have a fixed line. So same as we saw for QPSK and BPSK or PAM, same thing. QPSK, you could shift in both the IQ channel, but for PAM you only have I channel. That is why it was giving better. Same thing is coming here, but here it is in terms of codes. So this one point is ended. If anyone has question, you can please ask. So then we will move to generalized development of transmit diversity code. If you have questions, you can ask.
सर एक चीज थोड़ी सी कंफ्यूजन वाली है सर, जो पावर के ऊपर आपने डिस्कस किया है अभी के पैम और जो रोटेशन के केस में रोटेशन को पावर कम चाहिए सर, इसकी बेस थोड़ी सी दोबारा सा समरी सिर्फ बता दीजिएगा।
अच्छा चलें ठीक है, आप अपने आप को म्यूट कर दें ताकि वो आवाज कम सुने। सॉरी, प्लीज म्यूट योरसेल्फ। देखिए ना I might not have used this explanation to give you another view. Even this explanation was enough. Thus, probability of PAM is bounded by 5 times probability of rotation. Rotation is bounded by a factor, but PAM is 5 times greater than that, 75 and 15. All right. So you can see rotation is better. Okay. But I tried to explain the book words. And why I was trying to explain the book words, because when you are discussing communication schemes and communication systems, you try to save the transmit power, because transmit antenna needs power. You need to give a power to the transmit antenna so that when you get the receive signal, because any channel will give a drop, will have a drop. For example, if my transmit signal is 40 dB, but the drop is of 20 dB, so the signal that I will receive at my receiver will be of 20 dB only, 40 minus 20. Okay. So if you are able to give diversity gain or coding gain, so instead of sending the same signal through 40 dB, you might send the same signal to 20 dB. Because of the diversity and other things, you are actually increasing the received power without increasing the transmit power. So saving the transmit power is one of the fundamental, fundamental quality points or good points of a system if you can save your transmit power. Okay. The same thing we are trying to explain, that you can write the if you equalize the product distance, okay, then you can actually see, because actually product distance is actually making all the difference. Okay. But if I deliberately equalize it, then I can see that I require less power for rotational and for PAM to get this, it has to decrease its power. All right. And for rotation to get this, okay, it has to increase its power. So it explains that actually rotational is taking a power of a factor less than under root 5, okay, of a multiplication factor less than under root 5. So I think we can move forward. So what are the
thank you very much.
Thank you. So what are the general rules for time diversity code design criteria? So again, just a revision he is saying. So you say, let us say I have this output, this is my signal, this is my channel, all that which we have done. But now we have some, some repetition or some rotational or some any coding. So, this X is coming L times. So I say I have these code words, M code words. So I normalize these code words. Now you will say, sir, we are not understanding how you are linking this with our previous explanation. Okay. So this is a valid question. So I have actually done this here. Sorry. So actually I have not done this. So I will try to explain. This is the same thing. Don't get confused. So I will try to share, the stop sharing. Share, the equations. They are. Yes. So if you could see here, yes, I could rotate it like this. Now please see. Same equation as I showed you in the book. Now we had a steady rotational code. What is the value of L for rotational codes? Yes, it was 2. Length of my code was 2. All right. How many codes were present? Yes, they were 4. All right, no problem. So I had a 2 code. Okay, and code could be AA minus AA minus A minus A minus AA or A minus A, whatever. But it has to be a 2 length code. Once I detect a code, I will get 2 symbols. M was equal to 4. So I just put these values here, 4 into 8. Now summation xi mod square. Now, first of all, what is my xi? So it will be, all the symbols, x1, x2, x3, x4, all the 4 symbols. So x1, let us say I take xa. All right. So what is my XA? So XA was this. Okay, if you could remember. Everyone remember how did we got this XA like this? All right, or should I repeat this from the last lecture? You know, we had XA, XB, XC, XD. XA was equal to R into AA. So you multiply, you get this thing. Does everyone remember? Everyone remembers, all right? I can move. Anyone can answer. Do you remember how XA was equal to this thing? Or not remember?
सर ये सिंपल रोटेशन वाला मैट्रिक्स लगा के रोटेट लगाया साइन और कॉस की वैल्यू जो एंगल के साथ रोटेशन है बस ये ओके है
ठीक है ना समझ आ गया आपको ठीक है ना तो I found its mod square this will be square of this term plus square of this term so this term plus this term your minus a minus b whole square a plus this cancels so इसको भी हम मतलब कि you can right so a square plus a square this becomes 2a square so this was a square this will also be a so this become 2a square so I divide this by 1 over 4 into 2 4 are the symbols 2 is the length 8 and 2a square all the if you calculate the x mod square of all the symbols it will come out to be 2a square 2a square into 4 8 8 it cancels a square so the the energy was actually a square but here we say that we normalize this we say a square is equal to 1 so S and R instead of a square n naught is actually 1 over n naught this is what he is saying. So we have normalized this, all right? So what is the union bond overall property Farad? So here I have one mistake in this book. Okay, you can call it a mistake, but I think we should call it a mistake so that everything is properly related with respect to mathematics. All right. Now, what is the union bond? Actual union bond. Actual union bond. If you want to learn about the actual union bond is, if you could go into the digital com book, there you will see the definition of actual union bond. And if you want the reference, I have actually saw the before I was preparing for this lecture. So I deliberately went to that page and noted the actual definition that if someone wants to have a clean concept with respect to mathematics. So it is given in page 184, equation 4.2, digital communication, John Proctor's 5th edition. Okay. So you can see there actually there you will see. So it is actually 1 over m. All right, not problem, no problem, 1 over m. But so here he is saying it is probability of xi confusion with xj where I is not equal to j. All right, but there it is actually two type of summation. All right, one summation will be right xi with xj as given here. Okay, but the another summation will be for all xi symbols. Okay, now here he is saying that is as we said is there any xa confusing with xa with xb, xa with xc, xa with xd. All right. But in actual definition, it will be no XA with XB, XA, but also XB with XA, XB with XC, and XB with XD. All of the probabilities will be there, confusions. And then you have 1 over m, no problem. But here, if you are just summing probabilities of only one, only XA with XB, XA with XC, not summations of other confusions, then you shouldn't put 1 over m theoretically. But it is a bond, you can put 1 over m, but this is proper mathematics that tells us it is an error. 1 over m should not be placed. So if you want to place 1 over m, then you should have double summation. Okay, if you have single summation, don't put 1 over m. And actually you can see in the book, then when we started with union bond, so there was no 1 over m here. If there is 1 over, there should be also 1 over 4 here, but he is not given 1 over 4 here. That is why this equation was, earlier equation was proper. More, both are right, but this is more proper, clean mathematics. Now that each probability, okay, what is each probability? Again, we have driven that each xi is actually, you know, it could be two symbols. If it was 2, it was 1 over x SNR d1 over 4, as we saw here. It's the 1 mod square 1 over s, no problem. So, but if it is length 10, this will come 10 times, not 2 times as we saw in our proof. So this is all right, no problem. Here SNR is already normalized, so we have deliberately made a square to be 1 so that SNR is 1 over n naught. So we know that diversity gain is actually controlled by this difference, or difference in the code words. So this difference in the code words, okay, this is Lij, difference in the code word, this is Lij. So if I assume that Lij is equal to L, so all code words are different, okay? Okay. Their values are different, okay? All code words, okay? If they are different, then in that case, Lij is the number of complement where the code words are different. So if I say that all of them are different, so Lij will come out to be L, okay, because all of them are different. For yes, for all I, yes, I not equal to j, then the code achieves full diversity L of the channel. So yes, definitely, when you have maximum value, you will be getting all the SNRs will be there. Yeah, because you will have d1 square also, d2 square will be present, d3 square, dl, let us say L10, all their values will be present. Okay. If any one of them are same, you know, 1 over SNR will go away. So you will not have 1 over SNR L, but you will have 1 over SNR L minus 1 or L minus 2, depending if any of them are same. But we are assuming, as we saw in rotational codes, that there is some distance. They are placed separately. There is some value, some distance. So they are not 0. So L, right? So for, you know, if I I put this value here, 1 over m, let us say neglect this, so this, there's no 1 over m here, and I put this value here. So for larger, if SNR 1 is very small, so you know 4 goes in the numerator, so you have 4 times L, all right, SNR times L. So you will have 4 times L come out of the simulation. SNR will go L, okay. Del Ij is the the coding wo hai distance between relevant ports, okay, and all of them are present. So you know L times is already there. This is the minimum, the minimum thing. So first we have summation. Once we say minimum, then you have to add them. As we add there, we added 3 times 16, 3, 48. So here again m minus 1, 4 minus 1, so 3 multiply. So you will get that thing. Okay. So you know where delta j is actually the distance. Okay. For any code, L1 is equal to L. So for any 2 different codes, I just take the different symbols one by one and I calculate. So I will get the total product distance. Okay. So it is a product distance between xi and xj, right? जैसे हमने किया d1 mod square d2 थी वही चीज है. फर्स्ट का आ गया, ठीक है ना. First when you will have L is equal to 1, L is equal to 2. So one value. Then you will have multiply by L is equal to 2, L is equal to 2, I2, J2, D1, D2, D3, जितने भी हैं, you can product and you will get this value. So we have in general defined general values of any transmit diversity scheme code design criteria. So rotational code exploits time diversity in fading channels, as we have just learned. So it codes in an intelligent fashion. So and exploiting time diversity, it is also giving us the famous coding game. But if it is not a fading, let us say it is an AWGN channel, then rotation will not affect, because Gaussian noise is invariant to rotations. Okay, if you could remember, this was the property of Gaussian noise. Okay, so if you could see, we in the last previous lectures before midterm, we learned invariant property of the Gaussian random vector. The same thing is there because Gaussian noise is invariant, because it is, symmetric with respect to its circle. But other codes that are designed for AWGN, okay, right, like linear block codes, convolution codes, they can be used to extract time diversity in fading channels when combined with interleaving. So we will be learning what are these linear block codes or convolution codes. But if they are used, they are actually for AWGN channel. When you don't have HX, HX plus W, when you just have X plus W, AWGN channel. Okay. Okay. They are used for those channels. Okay. But we can use them, okay, to get time diversity in fading channels when we use interleaving. So we will learn about them. Achha. So what is the diversity gain of a linear block code? Okay. So it is a minimum Hamming distance. Okay. So here we will first of all try to share some important information. Let us go to digital communication book. So now we are studying about channel codes. So this is 5th edition book. You can see all of this. This is codes, 5th edition. Book is in our reference. Very, very famous book. It is called the Bible of Digital Communication. Saying that channel codes are actually of two types: block codes and convolution codes. So what is the basic thing? Basic thing is that you have a k length input information sequence. It is mapped to a n length code word. So n is always greater than n. So code word is always greater than in terms of length, than the information sequence. Okay, then you can send this. So block codes are memoryless. Okay, so memoryless means whether you have one bit, you have one k length code, a k length input. It will give you a certain n length code word. Okay, so for any k bit you will have a different n bit. Okay, so you don't require any memory because they are memoryless. Okay, coding scheme defines the mapping. The resulting code word is only dependent on the current k information, independent of all the code words transmitted before. This is called memoryless. So memoryless means that whatever the k bit comes, you will just see those k bits, give it the n bit coded output or the code word. Okay, you don't have to see, Hari, what was the state of my coder, what was the previous k bits, what will be the next k bits. No, just send. These are called block codes. Okay. The second things are called convolution codes. Okay. So in convolution codes, actually it is more complex. Okay. And the k bits they enter. Okay, you have n binary outputs. Okay, but they depend on the state of the encoder. Okay, there are finite states. Okay, and the n binary outputs or the coded word and the next state of the encoder will depend on the previous state and the k input bits. Okay, so this is this figure. And this is a convolution code. So every time k bits enter here, okay, all k bits they go out. So rest of these bits, they you can add them in any fashion. Okay, these are your output functions. So they will be giving you n outputs. For every k entry, you will get n outputs. That is the coded output. Okay. So here you have actually capital K stages, 1, 2, 3 up to k, and each stage is of k size because each stage can take k bits. This is one set of explanation. Okay. So we define the code rate of any block or convolution code, and that is k over n. So input over output. So it is always less than 1, as you can see. So these are some of the definitions that the book has discussed. Hamming distance. So what is the Hamming distance between two codes? So it is a measure of the difference between code words, the number of corresponding elements or positions in which they differ. So if I have two codes, so you just take the code words as 1, 0, 1, 0, 1. So at the point where they differ, okay, so that will give the measure of that difference will give us a Hamming distance. So minimum distance of code, the smallest value of the set for m code words, or the minimum distance for all code words, between the minimum distance between any two code words, that will give you the minimum distance of the code. For convolution code, we have minimum free distance. This is equal to minimum distance of the code. So here he is, you can see here, diversity of a binary linear block code idly interleaved is simply the minimum Hamming distance. So you can see Hamming distance is the measure of the difference, and the minimum Hamming distance, and free distance is also the minimum distance. So yes, that will give us the diversity gain. So as we actually saw previously, that the difference that was determining the, if there is no difference, diversity gain will decrease. So same thing he's saying here, that it will depend on the distance between the codes. So he is, you can formalize them to different types of channels: correlated, Ricean, or you can analyze them, but they will be all for exercises. So before we go here, we have also one other thing which I should have discussed before we go further. So if you take a look at chapter 8, of the same book, Digital Communication, structure of convolution code, same thing that we have discussed, all that. Now there are certain mathematics which actually the book discusses, so we have to understand before we go into that example. So there are modulo 2 adders. So if I have 1 plus 1, it is actually 2, but 2 is actually 0 in terms of mod 2. All right, but 1 plus 0 is 1, and in terms of mod 2 you will get 1. So they are mod 2 adders. They give you the remainder with respect to 2. And so one figure you can see, if someone asks you to draw convolution coder with K3 stages, each stage is of length 1 and 3 outputs shown in figure 8.1-2. This is the figure. So you can see there are 3 stages, each stage is a 1 bit. So you have two functions. One function is this, one output, other function is this, and the third function is this. So then how can I write these outputs? So you can see output 1 is just taking here, this will be 1 0 0. Output 2 is taking the outputs of 1 0, connecting the first and the last stage, and output 3 is connecting all the stages. It will be 1 1 1. I can also write them in terms of a polynomial form, which is this, because it was taking the first stage 1, first and second. So this is D01, but D0 plus 1 and third stage. So D0, there's no D1, D2. This is taking all the stages. So D0, D1, and D square. So you can also write them mathematically like this. Just, for sake of revision, so that we can understand this problem. So time diversity in GSM, a very, very important example. This also came, or its variants have came in PhD qualifying exam or last mid or final exam. So it is very important. It also relates, chapter 2 with this chapter. So, and also it is related to the commercial aspects of our course. So very good to learn about this example. So he said, let us say I have a GSM system, which we know it was a digital communication system in the 1980s. It was frequency duplex system. It has 2 bands, 25 megahertz bands. One was for uplink, another was for downlink. So the original bands were actually 890 to 915, 25 megahertz, and again 25 megahertz like this. Now each 25 megahertz band is divided into different 200 kilohertz sub channels. So this is actually 25,000. मतलब कि
स्क्रीन के ऊपर कुछ और सर पीछे नोट्स ही ओपन हो गया आपको।
मुझे आपकी कोई आवाज नहीं आ रही। आप कौन बोल रहे हैं?
सर सलमान बात कर रहा हूँ। स्क्रीन पे सर आपके वो नोट्स हैंड रिटन ही ओपन हुए हैं पुराने वाले, जो आप अभी एग्जांपल करवा रहे हैं उससे रिलेटेड कोई चीज नजर नहीं आ रही।
नजर नहीं आ रहा? ओह सॉरी यार, ये ही ना इसमें चक्कर जो है ना वो। सॉरी, आई विल मेक श्योर। स्टॉप शेयरिंग, देन शेयर। Thank you for clarifying. Now can you see the book, example 3.1? Everyone can see the book?
हाँ जी सर, अब आ गया, ठीक है।
Alright, take it. So this is the example I was discussing here. So this is a 25 megahertz band, uplink downlink, but 25 is actually to 25,000 kilohertz. All right. So this 25,000 is divided into 200 kilohertz bands. All right. So and each 200 kilohertz has 8 users. Okay. Then you get 200 kilohertz is allocated to one user in time division. In time division. Okay. Time division. So once one user will have 200 kilohertz, then the next time slot other user will have 200 kilohertz, and so on and so forth. Now, so each user is given a time slot with which it can utilize the 200 kilohertz band of 577 microseconds. All right. And now, so one user will be given 577. So once this time is over, its time is finished. The next user will be given the next time's slot of 577. When its time is up, it will be given to the third user, so on up till to the 8th user. So if you multiply 577 by 8, roughly you will get a value of 4.615. This is the frame length. One frame is this. One frame consists of 8 time slots. Each slot is of each user, and each slot is of this much microseconds. In 2G, we only had voice. We don't have video, as you know all of that. So in the voice, what was happening? that your voice is coded by a speech encoder into speech frames of length 20 milliseconds. So voice encoder will actually 6 to 5 minutes for 10 minutes. I will just let us try to cover up till this point. All right. So because it's difficult, and then we can repeat from this paragraph in the next lecture. Okay? Just bear with me for a small. I know it is Zan time and time is almost up, but just to complete our discussion. So frame is this. Each frame consists of 8 slots. Each slot is like this. Now, on the other hand, the voice of each user is actually encoded by a speech encoder into length of 20 milliseconds. So actually, your total frame is of 20 milliseconds. All right. Now the bits in each frame are encoded by a convolution code rate of half. So for each one input, you're getting 2 outputs with 2 generator polynomials, this and this. Achha, if I ask you to draw D4, D3, can you draw D4, D3, D1? Provided I tell you that the, let us say, coded is the case 1 and is 2. So you can draw this. Everyone is hearing me. I think you are able to, you can draw these convolution code polynomials in terms of their diagram. As just we have seen, 4th stage, 3rd stage, 1st stage, right? Each stage is of 1 like this. So you can draw this. Okay. So so the each bit in speech frame is, after this thing, it is further encoded by this, and each frame is of length 456. So each frame is actually of 456 coded bits. Each 20 millisecond frame is of 456 bits. Now, so what I will do with this 456 bits? Okay. So what I do, I take these bits, 0, 8 bit, then I will take 17 bit and so on, put them in the first time slot. So I know my frame is of 20 milliseconds and I just have 577 microseconds. All right. So I will divide it into, time slots. All right. Like this. So then the next, it will have 1/9 and 449 and so on and so forth. In my first times, I'll just put the first bit, the 8th bit, 17th bit, and up till the bit. So be 5, whatever the last first bit, which is for the 448 bit. Okay. So this will have the first and 0th and all the bits for the first user, 0th user, first, and all that. So in the second frame, I will put my second bit and so on and so forth. Second bit, then my 18th bit, and so on and so forth, like this. Okay. So one time slot covers this much. One time slot is this much. All right. So roughly, 8 time slots will be, but this 33 or something, approximately 40. And this is just tolerable for voice. And 8 time slots are shared between 2 20 ms speech frames. So 8 time slots, 1 time slot is happening after every 4.6. 8 is approximately 32, 33, 34, or approximately 40. So they will require 2 speech frames of 20 milliseconds. 220 milliseconds. And this is again summarized here. So this is my user frame. All right. So I will put this in this first one. Then you can see all these bits will go in the second, third, fourth, like this, and the eighth one. Then the ninth will come here. Then the all other will go there, and like this. In this way, the bits will be interleaved. Okay, in different slots. So this is the first frame. First frame, I will have the first slot, the eighth, and so on and so forth up till the end. Okay. Similarly, like that. So all the two speech trains, 40 milliseconds in this way will be divided like that. Oh. So interleaving structure is similar in 3 points. You can see the figure. So I will end the lecture at this point, but I will again, this last paragraph I know is difficult. I will again try to explain this from another point of view, so that you know every one of you is understanding. Okay. So. So we can mark our attendance. So how many attendances are there?
स्क्रीन नजर आ रही
स्क्रीन अपना, हाँ वो मैंने स्टॉप शेयर कर दिया ना। तो अब तो अटेंडेंस लगा रहे हैं, तो मैं आपको ना वो मैं सोच रहा हूँ वो शेयर कर देते हैं LMS वाला, ठीक है ना, ताकि आप सारे अटेंडेंस भी लगा लें, आपको नज़र भी आ जाए। लास्ट टाइम वाली मैंने भी लगा ली थी, वो भी मैं आपको शेयर कर देता हूँ। मैंने एक्चुअली वो भी रख ली अपने पास, ताकि वो भी आप देख सकें। लास्ट टाइम की अटेंडेंस में कोई प्रॉब्लम हुआ तो वो भी आप देख सकें। और जब तक ये LMS लिखता है मैं आपको उसकी वो शेयर कर देता हूँ अटेंडेंस। So I think everyone can see the attendance. Okay. So you can see the last attendance is as follows. Okay, I tried to put absent, all of them that were present. I have I think if you can check here, I think everyone is present. ये वो शकीर अहमद साहब का मैंने present डाल दी थी, so that there is no problem. All right. You can check here. I will also put this order so that there is no problem. Now I will share the LMS account where you can see your attendance. So I think you can see your LMS accounts. So here I go here. So today is 17th. Haji, 19 PhD 5 is present.
Present, sir, present.
1835.
Yes, sir, present.
1830. Who is
Present, sir.
1835? Who is
Sumair Khan.
1835?
Sumair Khan.
ठीक है। All right, good. So let's go further. All right, 35 है. 1836 present. अच्छा 1837. 1839.
Yes, sir.
1839. Who is 1839?
Waqar Zaman.
What is your email address? What is your यानी कि signing name?
Waqar
Zaman.
Zaman
All right.
so
Yes,
at the rate
yes,
gmail.com.
yes. Waqar Zaman. Yes, I have just seen. Thank you. Thank you very much. So 39 is there. 1842. 1842 is present. All right. 1862. 1863. 1863. 1941.
Present, sir.
1941. अच्छा 41.
Present.
1942.
Present, sir.
1941 हो गया. All right. 1943.
Yes, sir. Present.
1943. 1946.
43.
Who is 1946?
शकूर अहमद सर.
हाँ शुक्र है. ठीक हो गया. ओके आप हैं. ठीक है present. 1 2 3 4 5 6 7. Two other students are missed. Who are the students who are missed? Again, I'm giving you chance. You should speak for your own selves. Otherwise, you know, we are getting complaints that students they log in but they don't attend the class. So you know, attendance will not be marked like this. You have to speak up.
Amir Hamza, I think. Amir Hamza.
All right. Very. Are you there? Please speak up. I know his roll number, his name is here, but he is not speaking up. Amir Hamza, are you present?
सर अमीर हमजा बोल नहीं रहा, लेकिन अभी प्रेजेंट था वैसे वो
प्रेजेंट तो अभी भी है, मगर अटेंड नहीं कर रहे ना वो तो रोल नंबर में आ गए हैं, मगर वो उनकी आवाज नहीं आ रही. उनको होना चाहिए ना. और एक और भी स्टूडेंट मिसिंग है. 2 स्टूडेंट्स को अपनी आवाज, मैंने ये कहा कि अपना माइक्रोफोन वगैरह लगा के रखें. आपने प्रेजेंट बोलनी, आपसे सवाल पूछे तो एक क्लास हो रही है एक तरह से. इट्स अ लाइव क्लास. यू शुड बी एबल टू स्पीक. Who is the other student who is missing? I've already told you that you should be present in the class. You don't just have to sign in and go away. So last chance, any 2 students who are there, they have the last chance to say their attendance. Otherwise, this will be finished. All right. So no one is saying anything. So we end this thing.
सर गुलाम मुस्तफा की कॉल आई थी, वो कह रहा था कि मेरा माइक का प्रॉब्लम है तो सर को बता दें.
अच्छा, मगर उनको फिर ये भी कह दें कि वो नेक्स्ट टाइम से मुझे डायरेक्ट कॉल करें. और दूसरा ये भी कहें उनको कि मतलब कि नेक्स्ट टाइम से अपना माइक्रोफोन ठीक कर लें. ठीक है ना.
हाँ वो
मैं
कह रहे
उनका
थे
लगा देता हूँ.
किया हुआ
क्या किया हुआ उन्होंने?
रीसेंट किया हुआ था वो बता.
एक मैं समझा आप क्या कह रहे हैं. उन्होंने रीसेंट किया.
जी
रीसेंट मतलब क्या होता है? रीसेंट किसको किया?
नहीं सर.
हेलो. अच्छा उनका क्या रोल नंबर है? हेलो. हाँ जी.
42 सर.
आपकी लास्ट टाइम और उनकी लास्ट टाइम भी मेरे ख्याल से ऐसी लगी थी अटेंडेंस, वो बोल नहीं सके थे.
हाँ जी, वो उन्होंने मैं चैट में अपना वो रोल नंबर ड्रॉप किया था.
जी. तो अब ये कि उनसे कि लास्ट चांस है. अब वो दूसरे ने नेक्स्ट टाइम मुझे डायरेक्ट कॉल करें, और अगर है तो इनडायरेक्ट नहीं काम चलेगा. और दूसरा ये है कि वो अपना माइक्रोफोन ठीक करें. ठीक है, क्योंकि इस तरह की हमें शिकायत है, स्टूडेंट्स लॉग इन करके भाग जाते हैं.
हाँ जी ठीक है.
ठीक है, उनको प्लीज बता दीजिएगा.
ठीक है. ये
तो आप देख
अमीर
लें
हमजा की
ऑनलाइन
वजह
में
से
तो.
कॉल आ रही है.
अच्छा, वो आपको कॉल क्यों आती सारी?
वो सर वो क्लासमेट ही है ना, वो जानते हैं मुझे, तो एक मिनट
अच्छा.
पूछता हूँ उससे.
तो उनको पूछे उनको क्या मसला है।
सर अपना नंबर आप शेयर कर दें, फिर आपको कॉल कर लेंगे।
हेलो
हाँ जी हेलो हाँ नंबर तो वैसे मेरा आपको पता नहीं नंबर, मगर चले अब नेक्स्ट टाइम से सबको क्या नंबर तो मेरे पे कॉल ही आती रहेंगी सारी, तो नहीं कहाँ से कॉल आ जाए। तो आप सबसे कहते हैं कि माइक इनका मैं भी लगा देता हूँ, मगर सबको कहते हैं भी नेक्स्ट टाइम से माइक्रोफोन जिसका नहीं होगा उसकी अटेंडेंस नहीं लगेगी। ये फिर हमने लास्ट टाइम इसको हम लास्ट भाई जहाँ स्टूडेंट को इंटरैक्टिवली प्रेजेंट करना चाहिए। हाँ जी अमीर हमजा का रोल नंबर क्या है? 36 है। अमीर हमजा का रोल नंबर क्या है?
36 है
का
सर,
रोल नंबर
36
क्या है?
36 1836।
सही है। हाँ लग गया ठीक है, मैंने सबकी लगा दी है, मगर नेक्स्ट टाइम से प्लीज हर एक को अपनी प्रेजेंस खुद से बोलनी है और रोल नंबर भी होना चाहिए, आवाज भी आनी चाहिए और उसकी अटेंडेंस वो भी होगी। ठीक है ये सारा होना है। Thank you very much Zakala, so we will meet in the next lecture on Monday।
ठीक है सर। सर वो अमीर हमजा का भी वो माइक का इशू है, वो बता रहा है मुझे,
हाँ
पता नहीं
मुझे
वो
क्या
क्या।
ये ठीक करा रहा है, अभी काफी दिन है, मंडे तक सही करा दें। ठीक है ऑल
ठीक है।
अल्लाह।